I've made an important discovery, all because I got curious to ask a friend what he's doing, and he told me he was working on the Lockridge device. Actually, he's working on a lot of things. And so I started working on it with renewed endeavor, trying to simulate it and think about it. And I'm starting to better appreciate Paul Falstad's simulator, his transformers. He calls them ideal. Now, depending on who you ask, you get different definitions of what an ideal transformer is. It fails to leak energy. It is capable of passing DC energy. But the Lockridge device is an exercise in critical thinking in as much as it helps you think about electricity in a totally new way. And so this is what I think, this is what I've gotten out of it. In that, when John Bedini describes, when he's interviewed by Anthony Craddock on what little we know about the Lockridge device, it becomes apparent to me that what it is an ideal transformer. It has, and what that is that you have a magnetic field inside the core of the transformer that is at right angles to the exterior magnetic field generated by the coils of the transformer. In other words, you have another set of coils inside the core positioned and arranged at right angles to the exterior coils. And so when we look at a transformer, we're shown the exterior coils, but we don't see any other internal coils. Why? Because what Paul Falstad has done is he has created an ancient, by today's standards, an ancient style of transformer that no longer exists. You can't buy it. And the Lockridge device artificially creates it. It's called eddy currents. So what I'm positing to you is the idea that eddy currents, when we allow and encourage them to occur in the core of a transformer, are nothing other than another set of an electromagnetic field, another instance that is at right angles to the exterior magnetic field. So it's crosswise. So if your core of your transformer is either a cylinder or a section of a toroid that we can say is a cylinder, even though it's a curved cylinder at that point, it's still kind of cylindrical because it's just a section. At right angles to that tubular section or entirety is another magnetic field inside of it at right angles going. So your north pole, let's say as an example, let's keep it oriented in the plane of a toroid. So let's say it's positive going out from the center of the toroid, while it's negative, the south pole is going in towards the center of the toroid. That would be like an example of one way to do it. You could have it the other way. You could have it go parallel or congruent to the axis of the toroid. But regardless, or anywhere in between, but regardless, it's at right angles to the surface of the toroid, namely the surface of this cylindrical section of a toroid, or the surface of a straight cylinder, for that matter, the cylindrical shape of the core of a transformer, if that's what it is, just a cylinder shape to its core. It's at right angles. Now, that's macroscopically, and that creates heat, which is the equivalency of an eddy current is heat. But you don't have to create the heat. All you need is the electromagnetic orientation at right angles to the exterior. So you have and so that equivalency of heat behaves like heat even though it's not. And it clones your energy in another medium. And when you clone energy in another medium, you create perpetual motion. The potential for a perpetual motion machine. All you need is a capacitor shorting out the two terminals of the two, let's say it's only two coils on a transformer, on one side of it, let's say it's standing upright, this cylinder you've wrapped two coils on, and so you short out the top end with a capacitor, the two terminals of the two coils. The bottom end, you can do whatever you like. You can put a load down there, your choice. So now you have a capacitor storing this cloned thermionic at right angle electrical energy, or eddy current heat equivalency, in the capacitor. You've stored it in there. And now you got feedback, because now you've got an amassment, an increase, an aggregation, an accumulation of voltage in the capacitor that now feeds the coils, the external field of the transformer, which in turn feeds the eddy current, that's the transformer coil, the miniature, inside the core of that transformer that's at right angles to the exterior set of coils. And now you've got a buildup of power, because you've effectively eliminated your losses, creating an ideal transformer. Because now you've understood what eddy currents are, and you've accommodated them in a Thevenin equivalency, in a circuit that's the equivalency of the thermionic result of eddy currents, so that you never lose them. You get to use them, captivate them, and put them to good use, and accumulate it. But you've cloned it in another medium, which you really haven't done, but effectively you have, because it's at right angles. Now, a friend of mine did do a transformer design that had its two coils at right angles to each other, but they were exterior to each other. And that was probably his mistake. He thought they'd had some potential, but he did not put one inside the other, and that was his mistake. When you put one inside the other, you create what used to be called, what are they called? It's kind of like a gyroscope, but not really. It's, what is it called? It's a globe. The old-style globes had these great circles at right, or, not congruent with the original, but different than it. It could be at right angles, it could be anywhere in between, and it was like a globe that was not really a globe. It was like a skeleton of a globe, defined by a minimum pair of circles, one intersecting the other, but at right angles to it. So that's what my friend failed to do. He failed to have them congruent with each other. At the very least, if you have it one inside the other, it's the same as saying they intersect each other, but at right angles, rather than being exterior to each other, which is not. He had a partial intersection, not a complete. To be complete, you have to have 2 points on each great circle interacting with each other. And in this case, for optimization, and you try to reach for symmetry, and so you have your contact points, your pair of contact points, farthest away from each other, which is 180 degrees. Now, if you take that at the microscopic level, those two intersecting circles that are at right angles to each other, that create the minimum definition of a globe or sphere, because now you have circularity going not just around, let's say, the perimeter of the Earth, the equator of the Earth, but now you have it going around the poles, going from one pole to the other pole and back again to the first pole. And so you've defined a kind of square or cube using only two definitions instead of three, 2 dimensions instead of 3, because it's circular. And so when you do a circle, it defines the circularity of the cross section of a tube, basically. So that if you move that circle along a line of movement that is goes through the center of that circle, and at right angles to it, you create a cylinder. Not a rhombic cylinder because it's at right angles to that movement. It's like taking a clock. You face the clock. You have the face of the clock facing you, and you move the clock towards you and away from you. And so you're defining a circle, or excuse me, a cylinder. Well, a dead clock. If the hands on the clock are moving, now you've got something else going on in addition to the cylinder. Now you've got a helical coil surrounding the perimeter of that circle. But be that as it may. So when you take this internal dynamic of a congruent circle at right angles to the first, your reference, your secondary circle is at right angles to your reference circle, and you take that down to the level of electricity, you know what you get? You get the same kind of thermionic cloning in another medium, namely thermionics, but it does not exhibit the same way. It directly translates immediately into negative watts, what Jim Murray calls reactive watts, the definition of the generation of power. And you're doing it without you're avoiding Michael Faraday's law of induction, so that you don't have to move a coil through a magnetic field anymore, because you've already exploded or expanded by thermionic expansion the amps away from the volts by 180 degrees. So whenever the volts are like negative peaking or troughing, the amps are doing the opposite sign. They're positive peaking or troughing. They're reaching their limit. They're maxing. So the amps are maxing, let's say negative, while the volts are maxing positive, and then the next half cycle they're doing the opposite polarity. They're maxing out with opposite polarity than the previous half cycle. And then they repeat themselves, alternating every half cycle. So in a sense, what the Lockridge device has done is created a skewed kind of alternating current in the context of DC. And it's able to do this because it pulses, because the brushes have been filed down so that they cannot reach more than 2 commutator plates at a time. They cannot reach 3. They can only reach 2. They can reach 1 if they're right dead center on the commutator plate, because that's as far as their width is allowed to go, so that intermittently they can hit only 1 commutator plate. But they can straddle 2 adjacent plates, but not 3, because they're not wider than a single commutator plate. They're slightly less than the width of a commutator plate. So they can only straddle 1 or 2 commutator plates at a time, never 3. And so when they're in the middle of a commutator plate, you get a pulse, or you get this sustension of a pulse. If your commutator plates are alternately on and off, and that's what the case is for the motor coil of the Lockridge device. So when it goes from one commutator plate to the next, straddling inside of it, not straddling between them, but centered in the middle of a commutator plate rather than straddling 2 commutator plates. When it goes to the next plate, if it's an off plate, and then the next plate after that is an on plate, and then an off plate, and an on plate, you get pulsing. You get an on-off switching condition. A square wave. But it's a pulse. Rather than the coils being on all the time, the stator coils, the electromagnetic stator coils being... No, excuse me. No, the armature, actually. Well, they engage, right? No, the armature is on every commutation. It's the stator coils that alternate. And Bedini said it was the motor coils that alternate, not the generators. The generator coils were on all the time. but they do pulse. So they pulse on and off with a very short pulse off, but a duty cycle, a very short duty cycle off for each cycle of commutator duration, which is a portion of the rotation cycle. But the motor coil goes on and off. So that just means, all that means is it's got a longer duty, a shorter duty. Well, what would have been one on square wave becomes an off, and so it kind of creates a very long off cycle. It's like a longer cycle of on-off because it's two commutator plates in length of duration rather than one. So it's got a square wave that's, the motor coil has a square wave that's twice as long in wavelength than the generator coil. And on top of which, the off portion of the duty cycle is much longer. It's like slightly more than 50%. While with the generator coil, the off time is like 1% or something. You know, it's very short. In any case, it's important that the arrangement of the four poles are such that because of the slots on the housing, two slots, grouping two stator coils on one side of a slot, or a slot on either side, and then two coils on the other, and one of each pair of coils, one is a generator coil and one is a motor coil. So now you've got one of those coils keeps going on and on with very short offs, and the other one has a very long off. But be that as it may, you've got an electromagnetic field that's at right angles to the exterior field. The exterior field is created by the trifilar coil that's wrapped around the whole housing. And then it's got a capacitor wrapped around on top of that to capture the physical dielectric field that's coming off of this thing, the voltage of the magnetic field, the voltage component. But it's also connected in parallel to the three trifilar coils, two of which are extensions of, one is the extension of, in series, a series extension of the generator coils that are making contact with the commutator, and the other coil, one of the coils of the trifilar coil, is a series extension of the motor coils when they're making on contact with the commutator plates. But the third coil of the trifilar coil is parallel to the other two in a electrical sense because it's connected to in parallel with the capacitor. Yet it's wrapped up in series with the other two coils as part of the trifilar coil. So we got a lot of weird things going on here. Magnetic, anyway. But then to top it off, the overarching idea is that the Lockridge device is making use of eddy currents in an electrical format, not in the format of temperature. It's strictly limited to remaining in the electrodynamic field of activity, electrodynamic behavior, or manifestation. It's still manifest as electricity, but it's behaving as if it were the thermionic result of, the thermal result of eddy currents, because it's at right angles. This is the whole problem with eddy currents, is that they're some angle other than of magnetic flow in the core of a transformer, some angle of movement other than what the coils are. And so they're kind of a waste of energy. But if we organize that waste and make all of it at right angles to the exterior field that's being generated by the transformer coils, Now we got something going on here that's very interesting. And it's not in the form of temperature excitation, heating up the core of the transformer. Now it's still in the guise of electricity, but at right angles. So it's like thermal result of an eddy current, and yet it's still electrical. It's the electrical equivalency of thermal accumulation, but it's cloning, because it's clone in another medium. When you clone something, you don't convert it. It's not subject to conservation of energy because you've cloned it. So you haven't lost any energy in the process. You've simply used the energy twice. You've used it as electricity, and you've used it as thermal behavior. And yet you keep the thermal behavior as electricity. So it's a very interesting idea, and this is the whole foundation. It's the whole foundation for an explosion is thermal excitation of the dynamite variety, not the nuclear variety. The dynamite variety, or the chemical explosion variety, is thermal. It's like exploding gasoline in your engine. It's thermal. But we've created an electrical equivalency by simply having another magnetic field at right angles to the first, resulting from the first. And if it happens at the level of electricity instead of this kind of roundabout way of doing things, then we get negative watts, because the amps are out of phase with the voltage by 180 degrees. And they no longer are sine waves, regardless of how they got started. And it's always gets started with a sine wave. So it isn't regardless, but despite the fact that it starts out as a sine wave, applied energy, the resulting energy is spikes that manifest at their peaks and troughs and disappear otherwise. So all we see on the oscilloscope tracing are the terminus of the positive ends of the spike and of the negative end. And we don't see anything in between because it does not exist in between. It's imaginary. It's in the counter space of the ether. It's represented by imaginary numbers. Yet all because we took this crazy idea of this Lockridge device of harnessing eddy currents down to the microscopic level of the behavior of electricity itself. And so somehow or another we've created a right angle electrical field at right angles to the first to cause electricity to literally explode. Ohm's law explodes so that amps are opposed to voltage by 180 degrees. It's literally an explosion of electricity itself at the level of atomics, at the level of electricity. It's almost nuclear in a sense when you think about it. But it's not the nucleus of the atom that's affected. Only the valence shell of the electrons of, let's say, copper in the wire. Or wherever it happens to be, the electrical behavior happens to be. It's always in the valence shells. Well, at least of a conductive medium. I don't know how it works with storage in a dielectric medium such as plastic or glass, so I can't say. In any case, and this is what Paul Falstad manages to do. He creates an ideal transformer that does not lose its energy because he takes eddy currents into account. And the weird ridiculousness of it is that he gets thermionic expansion, not only thermal expansion. I'm not sure what the correct term to use, thermionic or thermal. I'll use both, either one. He not only puts that in his transformers, but he puts it in his incandescent light bulbs, with a difference. In the case of the incandescent light bulbs, when they're thermal temperature increases, they start to light up. They go from red hot to orange hot, yellow hot, white hot. They're color-coded. They're called Kelvin temperature in Kelvin, but they actually have nothing to do with absolute temperature of Kelvin scale of temperature scale. They simply use that idea to rate their thermal increase and the color changes that go with it. And so when the temperature of the light bulb goes up, regardless of how it's measured, the resistance of the tungsten filament goes down. And that increases current, which accelerates the rise of temperature. Well, when the resistance goes down, your power level goes up. When the power level goes up, that benefits all of your adjacent components in your circuit, such as your ideal transformer is now getting fed more current. Now, it's capable of generating more current because of the eddy currents being generated by the right angle cloned electromagnetic field inside of its core. But now it's getting this feedback from the incandescent light bulbs just like what it does. Only it does it all the time because its internal resistance to eddy currents never changes. It remains the same. But it's getting this feedback from the incandescent light, and then it just escalates like crazy. Its own internal expansion as it is. And the whole thing blows up. The circuit blows up. All because of the load being incandescent light bulbs. If it wasn't for them, it wouldn't explode. It would just slowly continue to increase because of the nature of Paul Falstad's transformer model. And if you put a capacitor across one pair of terminals on one side of that transformer to store the voltage buildup, shorting out the two sides but storing voltage, you end up getting a slow but gradual increase of power. Prior to the light bulbs lighting up and accelerating the whole deal and blowing up the circuit. They just sit there, comatose, black light bulbs because they're not lit up, dark light bulbs. Anyway, this is my take on this whole deal. It's been years trying to figure this thing out. And I knew it would take years. It wouldn't be easy. I knew that. But here I am, homeless, with a filthy body that needs to be washed. But, oddly enough, not washing helps you focus. Because you're not distracted by oh, I'm clean now. I feel good. No, I feel rotten. And so you go into your mind and you try to ignore the body. You try to get out of your body and stay in your mind in a very big way. Because the body, it feels like shit. Being so covered with sweat and the clothes bouncing that back, echoing it back. Oh my God, it's like the circuit, It's like crazy what I'm going through here. Anyway, that's my take on why Paul Falstad's simulator is so easy to create over Unity. I mean, he gives it away by calling it, well, he's got ideal transformers. His singular inductors are not ideal, only the inductors on his transformers. And he has two transformers. He's got a center tap transformer with two coils on one side and one on the other. And then he's got a normal transformer with one coil on either side. Restricted to 2 coils or restricted to 3 coils, but nonetheless, they're ideal. And this is my way to try to figure it out. He incorporated the thermal behavior of eddy currents resulting from the encouragement of eddy currents into the electrical behavior of his transformer. So he never tells you they're heating up because they're not. Meanwhile, he's put it into the behavior of the light bulbs and he tells you, oh, they're heating up. And the resistance goes down. Now, does the resistance of eddy currents go down when the core of the transformer heats up? I don't know. It doesn't seem to occur. It simply heats up. In other words, it does not accelerate its rate of increasing its eddy currents. So I don't think so. I think the resistance stays the same. That's the difference between the transformer core model in his simulator versus the light bulb, the incandescent light bulb model. Now, I'm going to do an experiment tomorrow, or today, it's early morning. When it gets daylight and I get to go do it, I'm going to replace the load in my Lockridge simulation, replace the incandescent load with LEDs in pairs that are parallel, connected in parallel with each other, one facing one way, the other facing the other way, because I learned by trying to put diodes on the electrical load that it doesn't work. It has to be able to oscillate. It literally is oscillating, even though the circuit, it does have oscillation elements because it's got a capacitor in parallel to the transformer, and then it's got another inductor in parallel with the capacitor, creating its own little LC subcircuit between the two of them. So yeah, there's oscillations going on, even though it's supposedly modeling a DC device, a Lockridge device. So I don't know how realistic that is, how accurate, but I'm trying the best I can. Without that capacitor, it doesn't work. And Bernini said it's there, in parallel to the transformer coils, so it's there. And then it's got its own coil in parallel to the capacitor. So you see, I am doing it right, of course. So it does. So that's why the Lockridge device has to create pulses, because when it creates pulses, it creates oscillations in that parallel capacitor and the parallel coil adjacent to that parallel capacitor, which is one of the three coils of the trifilar coil. But it's connected in parallel, even though it's wound in series. It's wound in parallel. Actually, yeah, when you have multiple windings, they're all in parallel. What am I saying? Anyway, I don't want to confuse myself. Blah, blah, blah. So that's what I'm going to do. I'm going to replace the incandescent light bulbs with LEDs to see if I get the same result of the acceleration aspect, because I'm having a heck of a time regulating the damn thing. I can regulate it before the light bulbs heat up. Once they light up, the whole thing spins out of control and explodes in my face. And it's been very frustrating. But if I replace them with pairs of LEDs that are opposed in direction, they don't heat up. They don't reduce their resistance. As far as I know, the definition of an LED does not reduce its resistance when it heats up. And so it doesn't have a thermal index. It's simply on versus off. And that might work. That might create stability to the circuit. Now, in real life, the Lockridge device does not explode. But I did something different. Well, no, it doesn't even slowly increase to infinity. So that means that the Lockridge device is not purely an ideal transformer. It has its limits. It must be ideal to a point and no further. And then it leaks. Or it doesn't leak, it fails to embody, because it has a limited domain to its core. So the domain of the core of Paul Falstad's simulator must be infinite capacity to soak up eddy currents, and so it just keeps soaking them up. And then it transfers to the capacitor that's in parallel and stores more and more voltage that continues to feed the transformer with more and more voltage. So it has a positive feedback that just keeps escalating to infinity. But in a Lockridge device, that doesn't happen. It goes to a limit and stops. And so it must be because it has a limited geometry or a limited dimensionality to its core, its so-called core. And so it can only create so much eddy current and no more. And so that's why you can't exceed 300 watts, because that's the limit of its thermal expansion.